I want you to imagine, just for a second, that you are standing on the floor of a modern, highly automated factory.
Right.
Like the kind of facility that looks like something straight out of a science fiction film. If you look up at the executive dashboards, the ones glowing up in the C-suite, everything is green.
Oh, always green.
Right. The metrics show 99% uptime. I mean, on paper, it is the absolute picture of ultimate industrial efficiency. Everything looks just perfectly flawless.
Until you actually talk to the people on the floor.
Exactly.
Yeah.
Because if you log on to a niche operator forum or, check a specialized thread at 2 in the morning, you start reading the raw, unvarnished truth from the night shift workers.
Yeah.
They are sharing these stories about these million-dollar machines on the floor, the ones that are supposed to be the absolute pinnacle of automated quality control, and the open secret they're all talking about.
They're blind.
Yes.
Yeah.
These incredibly expensive machines are functionally blind.
It is it's a systemic disconnect between the boardroom and the actual physical reality of the factory floor. We are looking at a $1 trillion blind spot hiding in plain sight across global manufacturing.
$1 trillion.
Easily. The systems we rely on to guarantee quality are actively working against the people operating them.
Which brings us to our mission for today's deep dive. We are going to unpack exactly why traditional rule-based automation is just fundamentally failing the modern enterprise. And more importantly, we're going to explore this massive architectural shift happening right now.
Right, the move to edge computing.
Exactly. We're going to look at why something called Edge AI is quietly stepping in to replace these brittle, hand-tuned rules with genuine, localized intelligence.
It's a total paradigm shift.
It really is. And we have a fascinating stack of material guiding us today. We were looking at a manifesto on restorative engineering from deep tech analyst Prasad Banda.
Brilliant paper, by the way. So good. We also have some very telling data from AMD Machine's 2026 industrial forecast and the real-world deployment metrics of SwitchOn Inc.'s Deep Inspect platform. But, to really understand this shift, we have to strip away the corporate fluff and focus entirely on the raw data of the factory floor.
I think the best place to start is by looking at the illusion of perfect yield.
Let's do it.
Let's ground this in a really specific environment like the electronics industry, specifically the manufacturing of printed circuit boards, or PCBs.
Okay, so the green board's inside basically every piece of tech we own.
Exactly. Every electronic device you interact with has a PCB inside it, and it's covered in tiny, delicate components. To ensure those components are attached correctly, factories use automated optical inspection machines.
AOI stations.
Right, commonly known as AOI stations.
And according to the operator forums we were just talking about, these AOI stations are practically a running joke among the people actually tasked with running the line. Yeah, and to understand why it's a joke, you have to understand the core mechanical philosophy of how these machines were built in the first place.
Okay, lay it on me.
Traditional AOI relies on a method called hand-tuned pixel comparison.
Pixel comparison.
Right. Imagine the circuit board moving down a conveyor belt at high speed. The AOI machine takes a super high-resolution photograph of it under a strobe light.
Okay, got it. Flashing light, snapshot.
Then the software compares that live photograph against a golden template.
A golden template.
Yeah, it's this perfect hypothetical image of what the board should look like.
Oh, I see. So it sounds like the ultimate high-speed game of spot the difference. Like the machine is just looking for pixels that don't match the master copy.
That is the exact mechanism, literally. Manufacturing engineers will sit at a console and hand code specific rules for every single component on that board.
Wait, by hand? For every component?
For every single one. They tell the machine, look at this specific coordinate. If this cluster of pixels is this exact shade of gray, the solder joint is good. If the pixel value falls outside this incredibly narrow threshold, flag it as a defect.
Wow, okay, but I'm assuming the physical world doesn't really cooperate with a perfect hypothetical template? I mean, the physical world is messy.
It actively resists the golden template. And this is where we get into what we call the physics of false positives.
Physics of false positives. I like that.
Let's break down what actually causes these systems to fail. Consider the solder paste used to attach the components to the board.
Okay, the silver stuff.
Yeah, solder paste is a metallic alloy, so naturally it reflects light.
Right.
Now, over the course of a 12-hour shift, the ambient temperature in a large manufacturing facility is going to fluctuate.
Sure. Machinery running, doors opening.
Exactly. And as the temperature changes, the viscosity of the solder paste shifts slightly.
Wait, really? Just on the ambient temperature?
Just from the room getting slightly warmer. And that subtle shift alters how the paste flows, and more importantly, how it reflects the overhead strobe light when the camera takes the picture.
Oh, wow. So the temperature change in the room changes the way the light bounces off the metal, which changes the shade of gray in the pixel.
Precisely. And that's just the paste. Add to that the lighting itself. The overhead fluorescent or halogen lighting inside the inspection station degrades infinitesimally over a period of months.
Because it's just a bulb, it loses power.
Right, the lumen output drops. So now it casts a slightly different shadow than it did when the golden template was created 6 months ago.
Oh, man.
Or consider the physical substrate of the circuit board itself. Under thermal stress in the oven, the board can warp by like a fraction of a millimeter.
And the machine, because it's strictly following these rigid pixel rules, has absolutely no idea how to interpret those physical changes.
None.
It just sees a shadow where there shouldn't be a shadow.
Exactly. It sees the harmless shadow or the slight shift in reflection. And because the pixel value doesn't perfectly match the golden template, the software just panics.
It panics.
It halts the entire production line and throws a defect flag. It misses the structural context entirely.
Okay, I have to stop you there, though. Because you're describing a system that breaks because the room got a little warmer or a light bulb got slightly older.
Yeah.
These are multi-billion-dollar companies manufacturing these AOI machines. Surely they know about shadows and temperature changes, right?
You would think so.
So why haven't the legacy vendors just fixed the algorithm? Why keep selling a broken rule set?
Because you literally cannot fix a rule-based algorithm to account for infinite physical variance.
You can't code for everything.
Right. It leads to a combinatorial explosion. If you try to write a rule for every possible lighting condition, every possible angle of warpage, and every possible reflection of solder paste,
It would be endless.
your code becomes impossibly dense and completely brittle. You end up with a million lines of code just trying to define what a good solder joint is.
Right.
The vendors haven't fixed it because the fundamental architecture, the pixel matching itself, is just the wrong tool for dealing with the messy physical world.
It's like hiring a hyper-strict bouncer for a club.
Okay, I like this.
You give them a rule, right? You say, only let people in if they're wearing a perfectly pressed blue shirt.
Right.
So the bouncer kicks out a VIP guest just because they cast a weird shadow on their shirt that makes it look slightly purple under the street lamp.
Exactly.
The bouncer is technically following the rule, but he completely lacks the context to understand the intent.
He's missing the big picture.
And the worst part is, while the bouncer's distracted arguing about the shadow, the actual threat, like the person sneaking in through the back window, gets completely ignored.
Which is exactly what happens on the floor.
Because the data shows these machines aren't just throwing false positives, right? They're actually missing real structural defects.
That is the ultimate tragic irony of the hard-coded rule system. It is simultaneously hypersensitive to harmless variance and completely blind to subtle actual defects.
Like what? Give me an example of a real defect it misses.
Like a dry solder joint hidden under a warped component. The pixels might look okay from the top down, so the rule passes it, but structurally, it's a failure waiting to happen.
Jeez. Which brings up the next obvious question. If you are managing a plant, right, and you know this machine is a hypersensitive, rule-bound nightmare, why do you keep buying them?
Yeah, because these are massive capital investments.
Exactly. Millions of dollars.
Well, it all comes back to those dashboards we mentioned at the very beginning.
The green lights.
The green lights. Plant managers buy these systems based on vendor case studies that promise, 98 to 99% detection rates.
Wow, 99%. Sounds great on paper.
It does. And when the system is integrated into the enterprise resource planning software, the ERP, it paints a beautifully clean picture of production. The executives see high line speed on their monitors upstairs, and they assume the automated quality assurance is functioning flawlessly.
But that executive dashboard is completely ignoring the invisible labor constraint happening down on the physical floor.
Exactly.
The dashboard doesn't show the human cost.
Let's walk through what actually happens on the floor when that machine halts the line over a harmless shadow.
Okay, paint the picture for me.
The machine throws a red light. The entire line stops.
Everything grinds to a halt.
Right. And a human operator has to physically walk over to the station. They have to stare at a raw, grainy, black and white camera feed on a monitor.
Looking at the exact same pixels the machine just failed.
Exactly. And they have to use their human domain knowledge to realize, oh, that's just a shadow. The solder joint is actually structurally sound.
Because a human can recognize a shadow instantly.
We do it naturally. And then the operator has to manually press a button to override the machine's failure flag just to restart the line.
And according to those operator threads, this cycle repeats hundreds of times per shift.
Hundreds, sometimes thousands.
The management team sits in an air-conditioned office and calls this automated quality assurance.
Yeah.
But the operator on the floor calls it the blinking box that requires a permanent human babysitter.
And that babysitting entirely defeats the purpose of the automation.
Totally.
You invest in a machine capable of inspecting hundreds of parts a minute, but the actual throughput is bottlenecked by the human who has to constantly apologize for the machine's lack of context.
Sorry, the machine got scared of a shadow again.
Literally. It creates massive silent capital leakage. You pay millions for automation, but what you actually purchase is a system that generates manual labor.
It's absurd when you put it like that. So, okay, if the local machine on the floor is effectively blind, and hard-coded rules are a dead end for dealing with physical variance, why aren't we using the obvious alternative? Which is...
I mean, we live in an era of massive artificial intelligence. We have incredible large language models, vision models, sitting in massive data centers.
Right, the cloud.
Yeah. Why don't factory managers just stream the live camera feed from the inspection station straight up to the cloud, let a massive neural network figure out if it's a shadow or a crack, and just send the answer back?
I mean, it sounds logical, really.
That seems like the easiest fix.
Yeah.
ChatGPT for factories.
But the moment you try to stream a live factory feed to the cloud, you run face first into the unforgiving laws of physics. Physics and network architecture. The short answer is latency.
Okay.
The long answer involves really understanding the sheer speed of modern manufacturing.
Let's unpack the long answer. Because, pretend I have no idea how fast a modern surface mount manufacturing line actually moves. What are the physics here?
The AMD Machines 2026 forecast gives us a highly specific benchmark to really ground this.
Okay, what'd I say?
A modern production line in a high-volume facility can run over 200 parts per minute. 200 parts a minute.
Yeah.
That means the machine is evaluating multiple components every single second.
Exactly. When you do the math on that throughput, it means that for the inspection system to work without slowing down the line, defect classification has to happen in under 0.3 seconds.
300 milliseconds.
300 milliseconds.
Okay, so map out the cloud round trip for me.
Yeah.
Why can't the cloud handle a 300 millisecond deadline? I mean, my internet is pretty fast.
Think about the journey of that data packet, though. The camera takes a high-resolution image.
Right.
That image has to be compressed, sent out of the machine, across the factory's internal network,
Which is probably huge.
through the corporate firewall, out to the public internet, routed to an AWS or Azure data center that might be, 500 miles away.
Okay, yeah, that's a long trip.
Then the cloud server receives the image, unpacks it, runs the massive inference model, generates a decision pass or fail, and then sends that tiny data packet all the way back through that exact same labyrinth to tell the robotic arm whether to reject the part.
And you are saying that entire round trip cannot reliably happen in under 0.3 seconds.
It cannot happen reliably because factory networks are incredibly hostile environments for data.
Hostile how? Like bad Wi-Fi?
Worse, a factory floor is not a pristine, climate-controlled server room or your home office. You have massive electromagnetic interference, EMI.
Oh, right, EMI.
Generated by heavy motors, welding equipment, huge robotic arms swinging around.
I didn't even think about that. All that electricity messes with the signal.
Exactly. And you have physical bandwidth constraints. Wi-Fi networks in factories drop packets constantly.
So if you rely on the cloud for real-time process control, your production line is going to stutter and halt every time there is a network hiccup or a dropped packet.
Yes. Your multi-million-dollar line becomes entirely dependent on the fluctuating ping of a distant server.
That sounds like a nightmare for a plant manager.
It is. Cloud architecture is fantastic for analytics dashboards that update every hour. It is brilliant for storing historical data, but it is fundamentally broken for time-critical synchronous inspection.
Which means the intelligence has to live locally.
Exactly.
The brain cannot be in the data center. It has to be bolted directly to the machine.
Yes.
And according to the AMD forecast, this shift away from the cloud is exactly what defines the industrial landscape of 2026. This is the era of edge AI.
Right. Instead of sending the massive data payload to the distant compute power, You deploy the raw compute power directly to the source of the data.
Bringing the brain to the eyes.
Exactly. We are talking about specialized, embedded hardware.
So the sources specifically mention hardware architectures like the NVIDIA Jetson Orin platforms, Intel Meteor Lake industrial chips, and dedicated Qualcomm neural processors.
Right, these are absolute powerhouses.
So what does this actually look like physically? Like you walk up to this legacy rule-based inspection machine and do what?
You literally bolt a ruggedized, specialized AI module onto the side of the legacy machine.
Just bolt it on.
Pretty much. You intercept the live camera feed cable before it ever hits the old, brittle, rule-based software.
Oh, I see. You're hijacking the eyes.
Oh. You hijack the feed, you run that visual data directly into the localized edge module, which is running a deep learning model right there on the factory floor.
Okay, here is where we really need to get into the weeds, because I think this is the crux of the entire deep dive.
Let's do it.
You intercept the feed, you send it to this local brain. How does this localized brain actually change the inspection process? You mentioned earlier that traditional AOI uses pixel matching. What is the edge AI doing differently?
The fundamental difference is the shift from pixel matching to localized convolutional neural networks.
CNNs.
Right, CNNs. A rule-based system looks at a single pixel and asks, is the specific dot the exact correct shade of gray?
Right, the bouncer checking the shirt color.
Exactly. But a convolutional neural network looks at the entire image and understands structural geometry.
Structural geometry. Okay, break that down for me. Pretend I have absolutely no idea how a convolutional neural network operates.
Fair enough.
How does it see structural geometry instead of just counting pixels?
Let's use an analogy. Think about how you recognize a friend's face.
Okay.
If you use pixel matching to recognize your friend, you would basically take a ruler and measure the exact distance between their left pupil and their right pupil.
Okay, very weird, but sure.
Right. But if they turn their head slightly, or if they are standing in a shadow, the measurement changes. The distance on the 2D image is different.
Right, because the strict coordinates change.
Exactly. The rule breaks, and you have no idea who they are.
Even though it's obviously my friend?
Exactly. Because you don't use a ruler to recognize a face. You look at the holistic structure, the shape of the jawline, the context of the features, the relationship between the nose and the eyes.
Right.
That is how a convolutional neural network operates. It passes the image through multiple mathematical filters, which are called layers.
Layers, okay.
The first layer might just look for simple edges and lines.
Like where does the component end and the board begin?
Exactly. The next layer looks for shapes and curves. And the final layers combine those shapes to understand complex physical structure.
Oh, wow. So it's not looking for a specific color value at a specific coordinate anymore.
No.
It's looking for the physical characteristics of a healthy solder joint.
Yes. The Edge AI has been trained on thousands of examples of what a true cold solder joint looks like, and thousands of examples of what a good joint looks like under varying lighting conditions, with different solder paste reflections, and on warped boards.
Oh.
It has learned the underlying physics of the connection. So when the overhead light degrades in the factory and casts a new shadow...
The thing that broke the old machine.
Right. The AI recognizes the underlying geometry of a solid connection beneath the shadow. It ignores the superficial lighting shift entirely because it understands context.
That is a massive paradigm shift.
I see it as everything.
We are moving from a system that asks, does this image perfectly match the photograph? To a system that asks, is this component structurally sound? We are completely replacing brittle rules with context.
And that shift is exactly why Edge AI succeeds where traditional automation fails. Rules are inherently binary. They shatter the moment they encounter variance at the edges of their programming.
Because they can't adapt.
But AI models, when trained correctly on localized edge hardware, they absorb and handle that variance. They adapt to the messy physical realities that completely break a hand-tuned algorithm.
And because that AI model is sitting right there, physically bolted to the machine, you don't have to worry about the cloud.
Exactly. You are getting localized inference with sub-10 millisecond latency.
Wow, sub-10 milliseconds.
There is no cloud dependency, no network lag, no jitter from EMI. The line never stops.
Okay, the architecture makes perfect sense. Replacing a strict binary ruler with a contextual brain totally solves the shadow problem.
It really does.
But, understanding the theory of localized inference is one thing. How is this actually impacting the bottom line on the factory floor right now?
Let's talk about the money.
Yeah, let's talk about the economics of autonomous quality. Because according to the sources, 2026 is the tipping point where this stops being an R&D experiment, right?
Oh, absolutely. It has fully transitioned into the mainstream. And the driving force isn't just that the convolutional neural networks that got smarter, although they did, it's that the underlying hardware economics flipped dramatically.
Right. The AMD report highlights some staggering deflationary trends in the hardware required to run this.
The physical components have just become commoditized. High-resolution industrial camera costs are down 40% since 2023.
40% in 3 years. That's huge.
And the cost of edge compute, those ruggedized Jetson and Intel modules we discussed, has plummeted. But honestly, the most significant economic driver isn't the hardware cost.
What is it?
It's the deployment cost. Deploying these systems no longer requires hiring a team of PhDs in computer science to write custom scripts for 6 months.
Which fundamentally lowers the barrier to entry for, like, mid-sized manufacturers.
Exactly. You don't have to be a Fortune 50 company to afford this anymore.
The AMD report mentions that the ROI payback, period-like, the time it takes for the edge module to literally pay for its own installation through reduced defect costs and increased throughput, has dropped massively.
It really has.
It used to be an 18 to 24-month gamble, and now it's down to just 6 to 9 months for most high-volume applications.
And in the world of industrial capital expenditure, a 6 to 9 month payback period is not just a green light, it is a mandate to deploy.
You'd be crazy not to.
Exactly. That is why we are seeing rapid, widespread adoption across industries where the cost of a defect escaping the factory and reaching the consumer is astronomically high.
And we see a perfect example of this commercial readiness in our source regarding Switch-on Inc.
Right, Deep Inspect.
Yeah, their Deep Inspect platform just landed in Intel's Edge AI catalog. What does that actually signify for a plant manager? Like, why should they care about a catalog?
Being listed in that specific catalog signifies that the software is validated, hardened, and truly enterprise-ready. It proves that the technology scales.
It's like a seal of approval.
Exactly. And if you look at where Switch-on is actually deploying Deep Inspect, it isn't just printed circuit boards anymore.
What else are they doing?
It's fast-moving consumer goods, checking the integrity of packaging at warp speed. It's automotive manufacturing, using edge vision to verify complex weld quality in real time.
Oh, wow. Welds are notoriously tricky to inspect, right?
Very tricky, lots of variants. But these edge vision modules are consistently hitting 99.7% accuracy at full line speed.
That is incredible. But, I imagine there's still roadblocks.
Always.
Right. You can't just drop an evolving learning neural network into a highly regulated industry without someone raising a red flag.
No, you definitely cannot.
So what is the lingering bottleneck here?
Well, the bottleneck is no longer technological. It is purely regulatory.
Regulation.
Specifically, when you look at the manufacturing of medical devices and pharmaceuticals, you run into stringent FDA regulations.
Oh, I can imagine.
The most prominent hurdle is FDA 21 CFR Part 11.
Okay. For those of us who don't spend our weekends reading federal pharmaceutical codes, what does Part 11 actually require, and why does Edge AI break it?
FDA 21 CFR Part 11 is essentially the regulation that governs electronic records and electronic signatures.
Okay.
At its core, it requires strict audit trails and determinism. When a pharmaceutical company validates a quality inspection software, the FDA auditor wants to see a locked, static system.
Locked and static, meaning it doesn't change.
Right. They want proof that if you put the exact same pill under the camera 1,000 times, the software will use the exact same predictable logic to evaluate it every single time.
And a neural network, by its very definition, is not a static list of rules.
No, it is a dynamic probabilistic model.
Right, exactly.
Validating a model that is designed to evolve, learn, and handle variance against a traditional regulatory framework that expects static, testable, hard-coded rules. It's incredibly complex.
It's like they're speaking two different languages.
Totally. It creates immense friction between the old paradigm of legislating quality and the new paradigm of actually ensuring it.
So how is the industry getting past that? Because they obviously are.
The AMD forecast notes that precedents are finally being established. Manufacturers are deploying edge models, but they are locking the model weights so they don't learn live during a production run.
Oh, interesting. So they train it, then freeze its brain.
Yes. They validate that specific locked version with the FDA, and then they go through formal batch update processes to introduce new learnings later. So the regulatory path is slowly clearing.
Okay, let's bring this down to the ground level.
Okay.
If you are managing a plant right now and you are listening to this, you're probably thinking, This sounds incredible, but I can't just walk onto my floor, rip out my $1 million legacy inspection line, and cross my fingers that this new Edge AI actually works.
No plant manager would ever do that.
Right. The operational risk of touching the main production line is just way too high. So how do you actually prove this works without risking the factory's output?
This is where Prasad Bandey's manifesto on restorative engineering becomes an incredibly practical operational guide.
Right. I wanted to get into his work.
He advocates for a philosophy he calls fractured prototype discipline.
Fractured prototype discipline.
The core idea is that you must force the deployment of a reversible, completely low-risk validation test. And he outlines a very specific protocol to achieve this.
He calls it the 48-hour protocol or the ground truth vision audit.
Yes.
When I read this in the sources, I thought it was brilliant because it completely bypasses the risk of messing with the live production line. Walk us through how this audit actually works.
It is brilliantly simple. Step 1, you do not touch the main production line.
Keep it alone.
You leave the legacy AOI machine running exactly as it is, generating all its false positives, requiring all its human babysitting.
Okay.
Instead of intercepting the live feed, you take one of these localized Jetson modules and you hook it up to a standalone camera focused entirely on the rejection bin.
The rejection bin. So you are only analyzing the parts that the legacy machine has already decided are defective and kicked out of the line.
Exactly. You're operating in a completely safe sandbox. It's already garbage as far as the line is concerned.
Right.
Step 2. You feed the Edge AI model 500 historical verified images of actual ground truth defect.
Meaning?
These are images that a human expert has visually confirmed are true structural failures.
Okay, so you give it an anchor of what real failure looks like.
Yeah.
What is the test?
These set a severe, uncompromising boundary condition. The local edge model must be able to classify those known physical defects as they sit in the rejection bin with 94% accuracy within a 48-hour window.
It's the ultimate low-risk proof of concept.
Yes.
If the Edge AI fails the 48-hour test,
Yeah.
you simply unplug the camera from the rejection bin.
Yeah.
You've lost nothing but a couple of days and a negligible amount of capital.
Literally zero impact on production.
But if it passes?
If it passes, you now have irrefutable, highly localized data proving that the AI can catch the actual defects without being confused by the variance.
Wow.
You have established the baseline capability of the model using your own factory's physical data, all without ever stopping production. It entirely removes the corporate fluff and the vendor promises, relying strictly on raw, operational evidence.
That is so smart. Okay,
Yeah.
let's assume the audit is a massive success. You scale the deployment, the Edge modules are bolted onto the main line, the machines can finally see and understand structural geometry without throwing a fit over a shadow.
The line is humming.
What happens to the human operator? What happens to the person who spent their entire night shift tapping a screen to override the old broken machine?
And this brings us to the human element of AI deployment, which, quite frankly, is the most profound part of this entire technological shift.
I agree.
This is where Bond's concept of restorative engineering takes center stage.
Because according to Bond, this isn't just about maximizing throughput or fixing the factory, it's about the underlying philosophy of the technology itself.
Right. Bond's central mandate is that technology must be designed to restore human safety, capability, dignity, and operational agency.
Dignity. I love that he uses that word.
It's crucial. Think about the psychological impact of what the old rule-based systems did. They actively stripped the dignity from the operator.
Absolutely.
They took highly capable human beings, people with deep intuition about the manufacturing process, and turned them into mindless spell checkers for broken machines.
It is genuinely soul-crushing work. You are standing there in a loud factory tapping a screen to tell a $1 million box that it is wrong about a shadow hundreds of times a night, every single night.
It's terrible.
You weren't building anything. You were just compensating for bad code.
But when you deploy Edge AI, the job description on the floor fundamentally transforms. The operator is no longer there to clear false positives because the Edge model handles the routine variants, the lighting changes, the minor reflections flawlessly.
The machine finally handles its own business.
Exactly. The false positives largely disappear, so instead of a babysitter, the operator becomes a model supervisor.
A model supervisor. That's a great framing. But what does that actually look like in practice for a night shift worker?
Because the AI is confidently handling the noise, It only flags true anomalies. It only stops the line for the rare edge cases.
Okay.
Like, perhaps a completely new type of defect appears that the model has never seen before, may be caused by a bad batch of raw materials.
So the AI says, I actually don't know what this is.
Right. And the operator is called over to review this rare case. They use their deep physical expertise to determine what the anomaly is.
They investigate.
They investigate, they label this new variation, and they feed that ground truth data directly back into the local edge model.
So they are actively training the AI. They are the ones teaching the machine.
Yes. They are closing the loop. And because they are constantly feeding verified physical reality back into the local model, the system's accuracy compounds over time.
It gets smarter because of them.
The operator moves from being a passive, frustrated babysitter to an active participant in engineering the system's intelligence. It completely restores their operational agency.
That sounds like a beautiful utopian vision for the future of work. It really does.
It's the ideal state.
But I have to push back here, because we need to ground this in the reality of the current labor market.
Sure.
The sources bring up a massive roadblock to this vision. You are talking about asking night shift factory operators to supervise and train convolutional neural networks.
Yes.
Isn't there a massive structural skills gap that prevents this from actually happening? Like, how does a line worker know how to tune a model?
Your pushback is entirely justified. The skills gap is not just real. The AMD forecast explicitly warns that the chasm is going to widen significantly by 2026.
Right.
This is the uncomfortable truth of the industrial AI revolution. You are dealing with two completely isolated domains of knowledge.
Right. You have universities churning out brilliant data scientists who understand the math behind convolutions and backpropagation, but they have never set foot on a noisy, vibrating factory floor.
Never.
They don't know what a dry solder joint actually looks like, or how industrial grease affects a sensor reading.
And on the other side of the chasm, you have incredibly experienced manufacturing engineers and floor operators who know the physical process intimately.
They live and breathe it.
They can tell a machine is failing just by the sound it makes, but they have never trained a machine learning model, and they have certainly never written a line of Python code.
So the intersection between those two skill sets, people who know both deep learning and physical manufacturing, is remarkably thin.
It's almost non-existent.
So how are companies actually bridging that chasm? Because if you can't get the domain expert to talk to the AI, all this localized edge hardware just becomes a series of very expensive paperweights.
Exactly. Well, the companies that are successfully scaling this architecture are employing two specific strategies. First, they are heavily relying on accessible, low-code or no-code industrial AI platforms.
Low-code platforms.
The sources highlight tools like Cognex's Vision Pro VD or Landing AI's Landing Lens platform.
How do those platforms actually work to bypass the need for coding? Like, what does the interface look like?
They abstract away the complex mathematics and the Python scripts entirely. They provide a highly visual, intuitive user interface.
Okay.
A manufacturing engineer simply uploads images of the parts and then uses their mouse to literally draw bounding boxes around the defects on the screen.
Just drawing boxes.
It's just drawing boxes. The platform translates those visual annotations into the mathematical weights required to train the edge model in the background.
Oh, that's brilliant. So it lowers the barrier to entry so drastically that the domain expert can interact with the neural network directly using only their visual expertise.
Precisely. The domain expert focuses on what to teach the machine, while the platform handles how to compile the model.
That makes so much sense.
And the second strategy successful companies are using is a massive investment in internal training. They have realized that trying to hire unicorns, candidates who possess both advanced data science degrees and 10 years of factory floor experience, is a losing battle.
Because those people basically don't exist, or they're too expensive.
Exactly. Instead, they are taking their best, most experienced process engineers and teaching them just enough AI literacy to evaluate solutions and specify requirements.
They aren't turning them into programmers.
No, they are creating a shared vocabulary. So the floor operator and the external tech integrator can actually communicate effectively about model performance and data quality.
Okay, let's zoom out and look at the macro picture. We've established the hardware on the floor. The localized edge AI is bypassing the cloud, running fast inference, and replacing brittle rules with context.
Yes.
The software is being trained through low-code platforms,
Yeah.
and the human operators are actively supervising and improving the models.
The whole system is working together.
The factory is fundamentally changed, and the massive bottleneck of quality inspection has been broken. Which leads to the natural next question. If localized edge AI can perfect quality control, what else can this architecture unlock?
This is where it gets really exciting, because this localized intelligence acts as a foundational layer.
Okay.
Once you prove that local inference works for complex visual inspection, you can start applying that distributed compute power to more complex multimodal
Like
datasets.
what?
The 2026 forecast points to two massive evolutionary leaps that are unlocked by this architecture: the realization of true digital twins and the holy grail of manufacturing predictive maintenance.
Oh, let's tackle digital twins first.
Yeah.
Because frankly, that is a term that has been thrown around the tech industry for a decade.
A total buzzword.
Mostly, it seems to refer to glorified 3D visualization models that look great in a PowerPoint pitch, but don't actually do much on the floor.
Yes, the fake blue UI and glowing holograms that Bond explicitly warns against in his manifesto. But the 2026 generation of digital twins, enabled by Edge AI, has moved entirely past simple visualization. We are talking about feeding real-time, high-fidelity edge sensor data into closed-loop simulation platforms.
So systems like Siemens Accelerator or NVIDIA Omniverse.
Right.
So it's less like a 3D model and more like a highly advanced physics engine for a factory.
That is the perfect analogy. It is a physics engine. Because a true digital twin isn't just showing you what is happening right now, it is simulating the physical reality of what will happen if you change the parameters.
Oh, I see.
The AMD report gives a specific example of this virtual commissioning that is honestly mind-blowing.
Let's hear it.
Let's say you want to upgrade a robotic arm on the line. In the past, you would have to buy it, bolt it down, and spend weeks tuning it, losing valuable production time.
Right, trial and error on the live floor.
But with a true digital twin, you go into the simulation, you swap out the virtual robotic arm for the new model, and the physics engine calculates the kinematic constraints, the weight payloads, and the motion paths.
In real time.
In real time. The digital twin will predict the new physical cycle time for that entire production cell within 2% accuracy before anyone has even touched a wrench on the actual factory floor.
That is insane. That allows you to program, debug, and optimize the entire line completely offline.
Yes.
The report notes that companies are seeing 30 to 40% reductions in commissioning time for new robotic cells just by using this virtual environment. That is a staggering savings in capital expenditure.
It is huge, but, and this is a critical dependency, a digital twin, no matter how advanced the physics engine is only as good as the sensor data feeding it.
Which brings us to the second massive leap. Predictive maintenance.
Exactly.
Right. If you have distributed edge compute analyzing all these sensors in real time, you should theoretically be able to predict when a physical machine is going to break down before it actually happens.
Predictive maintenance has been the almost there technology of the industrial sector for over a decade. Everyone talked about it, but few did it well.
Right. It was always 5 years away.
But with the massive deployment of Edge AI in 2026, it is finally delivering consistent, measurable ROI, and the financial stakes couldn't be higher here.
Give me an example of the stakes.
The AMD report uses the example of a machine tending CNC, a massive drill or lathe that might run 20 hours a day.
Heavy machinery.
Very heavy. When that machine suffers an unplanned breakdown, the downtime costs the factory between $5,000 and $15,000 every single hour.
Wow. That is just bleeding cash. It ruins the production schedule. It delays shipments. It's a total nightmare.
So how does Edge AI actually solve this? You install comprehensive sensor coverage directly on the CNC machine.
Like what kind of sensors?
We are talking about accelerometers to measure vibration, ultrasonic sensors for acoustic monitoring, thermal cameras, and sensors tracking the electrical current draw of the motors.
That's a ton of data.
It is. All of that raw, high-frequency data is fed directly into a localized Edge AI module.
Not the cloud.
Not the cloud. Too much data, too slow. The Edge module processes the vibration frequencies locally. And because the model understands the structural baseline of healthy machine,
It knows what normal sounds like.
yes, it can detect the microscopic acoustic shifts and vibration anomalies that indicate, say, a bearing is starting to score.
Oh, like a tiny whine in the motor before it actually breaks.
Exactly. The Edge AI can predict a bearing failure up to 72 hours in advance.
Which changes everything.
Everything.
Because if you know the bearing is going to fail in 3 days, you don't wait for the machine to catastrophically rip itself apart in the middle of a high-value production run.
No, you schedule the maintenance during a planned shift change.
Right. You swap the bearing when the machine is already off. The report says this localized predictive maintenance is reducing unplanned downtime by 40 to 50%.
But again, we have to look at the prerequisite for success here. And this ties perfectly back to Bond's manifesto on restorative engineering.
How so?
You cannot just buy an AI module, bolt it onto a legacy machine with terrible historical data, and expect magic to happen.
Right. Bond emphasizes what he calls a Dieter Rams approach to system design.
Exactly. Dieter Rams was the legendary industrial designer at Braun, famous for his principles of good design, material honesty, functional clarity, and less, but better.
Okay, I know his work. Very clean, very functional.
Yes. Bond argues that this exact physical design philosophy has to be applied to the digital architecture of industrial AI.
What does material honesty actually mean when we are talking about data pipelines and edge compute?
It means relying strictly on clean, raw, unvarnished physical realities. No corporate fluff in the data. You have to invest in the unglamorous, difficult work of proper physical instrumentation and reliable data collection before you ever attempt to train an AI model.
You have to do the homework.
Right. Many factories try to build predictive maintenance models using old SCADA logs.
Let's break down SCADA. Supervisory control and data acquisition. These are the old systems that log basic machine states, right?
Yes, and old SCADA logs are notorious for having incredibly low polling rates. Maybe they only record a temperature reading once every 5 minutes.
Oh, that's not nearly enough data.
The data is dirty, it's incomplete, and it lacks fidelity. If you try to run an advanced neural network on spotty 5-minute interval SCADA logs without installing high-fidelity edge sensors, the model will fail entirely.
It's the oldest rule in computer science. Garbage in, garbage out.
Exactly.
But in the era of edge AI,
Yeah.
it becomes garbage in. Very fast and highly expensive garbage out.
Precisely. The organizations that are actually achieving these massive ROIs in 2026 are the ones that respect material honesty.
They hit the fundamentals right.
They get clean sensor pipelines, localized edge compute to handle the bandwidth, and accessible low-code training tools to empower their domain experts.
Okay, so let's synthesize the journey we've taken today. We started by looking at the fundamental illusion of perfect yield. We explored exactly why rigid, hand-coded pixel-matching rules are a dead end. They are brittle, they lack context, and they absolutely shatter when exposed to the messy physical variance of a factory floor, whether that's a temperature shift or a degrading light bulb.
And we saw how the initial attempt to solve this streaming data to massive AI models in the cloud was completely defeated by the uncompromising physics of network latency and packet loss.
Which led to the massive architectural shift of 2026. Edge AI, deploying the raw compute power directly to the physical machine. We explored how convolutional neural networks replace binary rules with an actual understanding of structural geometry and context.
Furthermore, we examined the profound human impact of this technological shift. By utilizing low-code platforms and adopting the philosophy of restorative engineering, factories are moving away from treating highly capable human operators as mindless spell checkers.
Which is huge.
It is. They are transitioning operators into model supervisors, restoring their operational agency, and utilizing their domain expertise to actively train the AI.
It is a massive systemic shift from passive, brittle compliance to active, localized intelligence, both for the machines and the people running them. So if you are listening to this right now, I want to turn the focus directly back to you. Look closely at your own industry. Look at your own daily workflow, your own team's processes, even if you are thousands of miles away from a physical factory floor.
You need to ask yourself the hard questions. Where are you relying on brittle, hard-coded rules that constantly generate false positives? Where are you, or where is your team, acting as a manual human spell checker for a broken, supposedly automated system?
Right.
Because if you look closely, chances are that is a hidden bottleneck, silently draining your capital, your throughput, and your team's energy.
Exactly. Find the false positives in your own systems. But before we wrap up this deep dive, I want to leave you with one final, slightly provocative thought to mull over as you look toward the future.
Okay, what is it?
We spent this entire time talking about decentralizing intelligence, moving the brain out of the massive cloud data centers and pushing it down to the specific inspection machine, the specific camera on the edge of the network.
Right, edge AI.
Right. But as these edge processors get cheaper, smaller, and vastly more powerful, we're going to see intelligence pushed down even further to the absolute smallest hardware components.
We are talking about neural processing units embedded right down to the individual sensor level.
Exactly. So consider this. If every single vibration sensor, Every acoustic monitor, every camera, and every individual robotic arm has its own localized, context-aware brain making micro-decisions in milliseconds.
Mm.
What happens when these distributed, highly intelligent machines start communicating with each other?
Oh, wow.
What happens when they start collaborating and optimizing the entire physics engine of the factory floor on their own, completely peer-to-peer, entirely outside of the cloud, and at a speed that human oversight can't even begin to track?
That decentralized collaboration is the true uncharted frontier of industrial automation. It's swarm intelligence on the factory floor.
It really is. So the next time someone tries to sell you on their perfect, flawless, rule-based dashboards, just remember the reality of the night shift operator. Remember the messy physics of the floor, and ask yourself, is the machine actually understanding the physical reality of the problem, or is it just terrified of its own shadow? Thanks for taking the deep dive with us.